In recent years, we witness a tremendous progress of AI, mainly thanks to the rise of large language models, with models such as Llama 3.1 and many more. To enhance the capabilities of large language models even further, a lot of research focus is devoted to find improvements in the training process of these models. In this video, we review a recent research paper by Stanford University and Synth Labs that suggests such a potential improvement that may become important in advancing AI a step forward. The paper is titled Generative Reward Models, and some of its authors were also part of the DPO paper, which is now widely used in the industry. Before diving to the method presented in the paper, let's do a quick recap for how large language models are trained. The first step is pre-training. Large language models are first pre-trained on huge amount of text to learn general purpose knowledge. This step helps the LLM to be good at predicting the next token in a sequence. So for example, given an input such as write a bedtime, the LLM would be able to complete it with a reasonable word such as story. However, after the pre-training stage, the model is still not good at following human instructions. For this reason, we have the instruction tuning step, where we fine-tune the model on an instructions dataset, where each sample from that dataset is a tuple of an instruction and a response, which we use as the label. After this step, the model is good at following instructions. However, in practice, top large language models continue being improved after this stage using feedback. A strong method of doing that is reinforcement learning from human feedback, or RLHF in short, where the model is trained on human feedback. Due to the challenge of gathering such feedback, we also have reinforcement learning from AI feedback, or RLAIF in short. The paper we review today is related to this final stage of improving the model using feedback, so let's expand our background a bit deeper on this phase. With reinforcement learning from either human feedback or AI feedback, we have a pre-trained large language model which we use to generate responses. The responses are then evaluated by human or by a different model in order to produce a data set of evaluated responses where each sample has an instruction, a negative response, and a positive response. We then train a reward model based on that data that learns to rank the LLM responses. Then the LLM is trained using the reward model, mostly via PPO, in order to yield outputs with high ranking. More recently, direct preference optimization, or DPO in short, was introduced with shared authors with the paper we review here. With DPO, the need for the reward model is removed, meaning we train the LLM using the feedback data directly without creating a reward model. However, based on recent research, solely relying on methods such as DPO without a reward model may not yield the best performance. So, for example, Llama 3 is using a hybrid approach of both DPO and reward model-based learning. The paper we reviewed today, Generative Reward Models, suggests a unified framework for RLHF and RLAIF to tackle two main limitations. One is that reward models struggle with out-of-distribution data, meaning that they do not generalize well when encountered with input types that were not part of their training feedback data. Second is that AI feedback may not always align well with human feedback. Before moving on, if you're getting value from this content, then please consider subscribing to the channel and hit the like button to help this channel grow. We also send 1-minute read summaries by mail about the papers we review here. You may find the link to join in the description of this video. Let's now move on to explain what are generative reward models and how they are created. In the first phase, we begin with the LLM that we want to act as a reward model, and we train it on a data set of human feedback. However, it is different than previous reward models since the reward model that we train is generative, unlike previous reward models. We can see what it means using the following figure from the paper. On the left, we have a Bradley-Terry model which represents the standard previous type of reward models. We see it gets an instruction and two possible responses as input. In addition to the LLM, it has an additional linear predictor head to directly return the probability that one response is better than the other. In the middle, we have a generative reward model. The input also includes an instruction and two possible responses, but here we do not have an additional head. Instead, the model should generate an answer indicator token that represents the preferred response. So we have the probability to generate an indicator token for each of the responses, and we prefer the one with the higher probability. On the right, we have another version of Generative Reward Model called Chain of Thought Generative Reward Model. As the name implies, in this case, rather than generating only an indicator token for the preferred response, the LLM is instructed to provide reasoning for the decision in addition to the indicator token. To choose the final preferred response, we may sample few reasoning traces and answers and decide using a majority vote. We now have a generative reward model which was trained on a human feedback dataset, and we continue to improve the model in iterations using a method called self-taught reasoner, or STAR in short. The way it works is that we prompt the model with inputs from the human feedback dataset to determine the correct responses and also to generate rationales for the decisions. Then, we filter out reasoning traces that did not lead to a correct response according to the labels from the human feedback dataset. This process provides us with a new dataset with reasoning traces, which the model is then trained on in a supervised fine-tuning process. We then repeat the process for a few iterations. We refer to the trained model as Chain of Thought Generative Reward Model STAR. However, there are samples from the human feedback dataset which we did not use here in case the model was not able to determine the correct answer. In order to use these samples as well, there are two suggested methods. One is to generate reasoning traces for these samples as well, but provide the model with the correct result as a hint, just asking it to create the reasoning for a known result. Then, we can enrich the data set we use in each iteration. Using this approach, we get another version of the model with a rationalizer suffix in its name. Another option is to use the rationales that lead to wrong judgments as another dataset and use a DPO like loss to punish the model for such samples. The name of this version of the model has a DPO suffix. Let's now move on to see some of the results presented in the paper. In the following figure, we can see a comparison between different versions of generative reward models and prior reward modeling methods. The results on the ultra-feedback dataset represent in-distribution data. We see that few generative reward model versions are competitive with the Bradley-Terry reward model. But when looking at the results on reward bench, which represents out-of-distribution data, the STAR DPO is significantly better than Bradley-Terry, so the generative reward model was able to generalize better for out-of-distribution data. The rest of the results to the right are subsets of the reward bench data grouped by categories. Thank you for watching and stay tuned for more reviews of AI papers.